Hello, I am actually filling in for Rick Avila, who just recently welcomed a new grandson into the world. So he could not be with us. And today I'm talking about the role of CT calibration, and I think it's a very relevant topic, especially in the context of the previous talks we just heard, as well as some of the talks yesterday. So this is a plot where we're showing uh, the volumetric change of zero change data. So this is nodules that are supposed to have zero change measured multiple times. And as you can see, uh, as the nodule size increases, the what we call the volume difference decreases. And this has implications for clinical interpretation. Essentially, what this means is the variation you see is not consistent, and it varies with the nodule size, and smaller nodules have higher variation, as you might expect. So nodule, the variation of the nodule size varies with decreases with size. So, but what we're actually concerned about are the nodules at the smaller sizes. So right here is 5 millimeters, and you can see there's roughly, up to a 70% difference in volume, which is fairly significant when you're trying to use this for determining, what to do next with participants, lung screening participants. This is uh, these numbers are the Kiba small lung nodule profile numbers converted into diameter. But basically, it's saying that this is at 6 millimeters, you still have uh, really large changes in volume. So, in light of this, I think the question is, first of all, how do you even measure uh, what? Sorry, so let me step back. So there are a couple of different factors that contribute to this volume difference or this volume variation. There's variation that's due to the scanner. There's um, contributions from the measurement method, either the algorithm itself or if you have multiple radiologists or sorry, different radiologists measuring the same nodule, the different experiences and biases of each radiologist. Um, but we've never actually had a good way of measuring what the contribution of the scanner is to this variation in the nodule measurement. And what Rick and his team have done is developed a automated and cloud-based method for measuring CT image quality. As you can, this is his Phantom, which has a couple foam cylinders of different density. This is what it actually looks like inside a CT scanner, and this is what it shows up as on the CT scan. And based on this, you would scan the Phantom, upload these acquired images to his service, and you would get a report back with very easy to understand results. And it would kind of tell you whether your scanner and your protocol meet uh, various metrics, including, bias and resolution. I think it's on the next slide here. Yeah, these fundamental CT image properties of resolution, the resolution aspect, the linearity, the image noise. And I think what's the takeaway point from this is that this provides a very quick and easy way of measuring these properties, which are really critical to know if you're trying to make accurate measurements. And the whole point of making better measurements is to have uh, to be able to provide the radiologists with a uh, more confident, more confidence in their measurements so they can make better recommendations for patient follow-up. What we had shown earlier was kind of the version 1 of the Phantom. He has this new version 2.1, which uh, this is a much bigger Phantom. Inside, you have different objects of different density, and on the outside, you have these plastic rings, of which you can kind of use a different number, and these uh, are essentially there to help model the effects of different patient sizes. So um, he's continuing to extend his phantoms to incorporate a lot more, uh, sorry, to incorporate a lot more different aspects, different impacts of sorry, different things that can impact both the scanner and the measurement. Um, so I think sorry. So with these phantoms, this I forgot to mention that this is very low cost. I mean, I think there are phantoms on the market today which cost several $1,000s and don't provide all of these different metrics that we're able to provide with these phantoms. And by just going through this process of scanning phantoms and getting results and then refining your protocol, we're able to help sites eliminate low quality scans. And this is not to say that, you know, scanner particular scanners or scanner manufacturers are bad. It's just that you can change the protocol, as Dr. Gibb showed us yesterday. You can make changes in the protocol to improve the measurement. So this, it doesn't take any new hardware. It's just, making better selections in terms of the acquisition protocol. And the second thing this allows is that you can actually quantify or understand uh, what changes in your protocol have on the actual measurement performance. Until now, that wasn't really possible, especially without having this easy to use, low cost phantom. Um, I think previously, you usually had to have a medical physicist interpret the scans. Um, and there wasn't really a consistent way that was done. But now anybody, just a normal CT tech could acquire these images and upload them into this service. And as we mentioned, this would help you optimize your acquisition protocol to improve your measurement. It also will actually let you monitor uh, the performance, the performance of your scanners across your enterprise and across time. Uh, there's nothing to say that your scanner will stay consistent over time. I mean, I think as um, part of the role of the CT tech is that they have to scan the phantom every day or every week to make sure some very basic things are remaining unchanged. But this goes a lot further than that. And in addition, many hospitals and hospital systems use a variety of different scanners, and this will help kind of allow you to uh, understand what the differences between those scanners are and try to harmonize your scan quality across your different CT scanners. And in the future, this will help us kind of determine better uh, follow-up times, possibly being able to personalize it based on for a particular patient. Many of the lung screening protocols have fixed time points. Either you recommend a 1 month follow-up or a 3 month follow-up. But the reason for a lot of those time intervals is not for any sort of physiological reason, but it's just to overcome this measurement uncertainty. Uh, Ideally, if you had a perfect measurement system and you could be confident that a 10% volume change was actually a 10% volume change, you would just say, hey, come back in a week. And if it grew in that week, then you would know that it's growing. But unfortunately, as I showed in the plots earlier, we have 70, 80% variation in the nodule volume. Um, so we set the follow-up times to try to overcome that inherent measurement uncertainty. So one study that we did with ELIC was looking at the looking at the performance of you're looking at the nodule volume size for lung cancer malignancy. And we looked at diameter, volume change, and volume change with only high quality CT scans. And what I'm showing in blue is the sensitivity and orange is specificity. And you can see that both the sensitivity and specificity included when you only looked at the high quality CT scans. Uh, Ilya spoke about this protocol optimization with the GE scanners yesterday. Um, and I'm going to just quickly summarize it for those who may not have seen it. The bias decreased by about 50% from just a standard Kiba suggested protocol to the optimized protocol. And the volume precision, which is the variation in volume measurement, also decreased by about 50%. So again, this is not with any hardware changes. This is just picking different settings for your protocol. And by having these calibrated CT scanners, this also helps to improve AI and in terms of improving the detection and measurement of small nodules and features. So think about you have all of these AI algorithms that try to determine malignancy based on radiomic features, but if you have this variation, in size, what does that mean for the variation in radiomic features? And so you can imagine that with a better understanding of and better image quality, uh, you can get improved AI results. Here is just an example of a scan on the left, which is scanning a star-shaped object. And you can see that you can kind of barely see these kind of just call them speculations. But with increasing the Z resolution, the dose, and the sampling, you can see very clearly what the object actually is. And so imagine you're doing radiomic features. These would be very clearly different. And this is the one on the right would give you a much better measurement. Um, this is, we looked at the quantitative results, and we found that the measurement precision improved by 650%, and bias was also improved by 600%. You can see in the 3D reconstruction here how much better the object looks when you're able to optimize the protocol. This is just some clinical examples. On the left is your unoptimized scan. On the right is your optimized scan. You can see, this nodule here, and all the vessels and all the surrounding structures look much clearer. Here, in fact, you barely, I mean, here you can't even make out these airways. I guess they're airways. Not entirely, sorry. I'm a scientist and not a radiologist, but you can see that these features are completely invisible in the left image. Again, much better, much improved image quality. You can see that there are these branches that aren't even visible on the left scan, and this bronchus. Thank you. So summary, CT calibration using these small lung nodule phantoms continues to improve, and it also helps to support investigations into the trade-off of CT dose and quality. Higher image quality obviously gives us better nodule growth measurement, and integrating real-time AI and calibration during the CT scanning itself has the potential to dramatically improve our nodule measurement. Thank you.